Okay, I guess we can start basically. Um, I was telling you, I found like a very nice topic to like at the first week was like the matrix that the answer completion problem. I mean, obviously it's like a long topic, so I was just going to give you kind of like the main ideas of some of the things that go, like that are that take place to solve it. Because I think they're kind of like interesting in their own right. In fact, I'm not sure if I don't get to kind of like cover everything that I should, but if for some reason I run out of time, I'll just finish guiding them on the EF notes and then share them with you so that you kind of like have references or something like that if you're interested. But like some of the proofs for these things that you kind of like read the original papers, they do involve a lot of like problems. So they're kind of like heavy theorems in the sense that they're definitely not like it does require like a best knowledge, but just like understanding some of strategy can be like a school really recently. So I didn't write everything, but I thought at least I'll was going to start like this by telling you a little bit of what's going on. So again, the setup is that imagine that you have a matrix, and for some reason, either maybe you have access to all the answers, but you don't want to use all of them, or maybe no, you don't have access to all of them. So I think the example I mentioned, which is one of these like famous examples for the matrix completion, was like this Netflix ranking problem where like the matrix, maybe the rows refer to the users, like and then the columns refer to the movies, right? And so an entity of the matrix, if you ask like the users to rank it at 1 to 5, and then like the entry, each entry of the matrix would be a number between 1 to 5. But sometimes some of the users do not rank the movies, so some of the entries are missing. Or you want to use a subset of the rankings, recommend for recommend movies to other users. Okay, so in this type of setup, like kind of the idea is that you kind of know certain entries of the matrix, which is what you see here. So kind of like just to explain what I wrote here. You have like kind of like the original input is that you have this matrix A, but not all the entries are known, or you don't want to use all of them, like it could be the or the one to use. Okay, and then so you just like access some of those entries or like do like a sample of like entries of the matrix, right? So that's what this omega set refers to. But just like the indices, right? Like the and no, this kind of like refers to the indices of the entries that were like observed, in quotes or like were sampled. Okay. So again, like if you just say how can you kind of like recover the matrix, if you don't have any other conditions, that's not like an interesting problem because, like, for example, if you just zero everywhere else for all the other ends. So of course, I just want to make it interesting, and kind of like the idea in all of the many of these problems is that maybe you want to try to find a matrix of the least rank possible that kind of completes it. So kind of like the goal would be kind of like to solve like the problem like this. You want to find a matrix that minimum rank with the condition that for those entries that were observed, they could match, right? Of course, you can imagine how this could be varied because maybe you don't want like that it matches exactly, but maybe up to some error, you're okay. So like then that's where you start throwing in all these approximation schemes. So I'm just kind of like giving you kind of like the ideal case scenario where like you want perfect matches, but like if you expected, I mean that wouldn't be so much with the Netflix case, but if it's kind of like you're recovering like distances between locations, kind of more like then there can be noise in the signal that you use to make the measurements between the distances. So maybe you wouldn't necessarily care too much about all the entries being recovered like, exactly, if there's noise or other things, errors. Um, okay, but so kind of like that would be the goal, kind of like a philosophical level, but then we have to get into like, the nitty-gritty of what this is actually doable, right? And the idea is that as stated, right? it's not that easy problem to work with, because the rank function is like a random function. So like, it basically just to give you an example. So yeah, you could think of the rank as a function, right? Like the input is a matrix, right? And it outputs the rank. In fact, like it's not your, not, I mean, it's real value, but you don't take lots of it into your value, right? It's like a two. Yes, right. Also, oh, if you want to, yeah, if you want to come here and you can take a screenshot of the invite information. Where do I have this? Sorry, give me a second. The meeting info. If you want to take, yeah, like come here, like yeah, this is like the ID and all of that, so that you can kind of like send it to him. Thank you. Yeah, sure. Okay, so what I was saying is that the matrix, right? If you think of the matrix as sorry, if you think of the rank as a function, right? Then you can matrix produces its rank, right? That function, well, first it's not even complete because it's discrete, right? It's the jobs. But even taking that aside, it's also badly behaved from like another perspective as in it's not even convex. So convexity for a function, I don't know. I think I had said it before, but I'll kind of like remind you what the definition was of a function being convex. F is convex if f of 1 minus t x plus ty is less or equal to 1 minus t f of x plus t f of y. So here, x and y are, you know, values in the domain of the function, right? So x and y here are in the domain of the function, and and t is from the convexity, the parameter that, because again, convexity involves like the segment between the points. So t is kind of like the, how much of it's what generates like the segment from x to y. It's a number between 0 and 1. Just logging. Can you hear me?
Hi, Professor. How are you?
Good, how are you? I was just, you haven't missed much. I was just telling them that, like, if you remember this matrix completion problem, where you're trying to minimize the rank, that the rank function is like not a very nice function, and then that's basically what I was about to explain why it doesn't behave so nice as a function of matrices. Um, but I'll be checking the chat. I mean, again, like you can unmute yourself if you have any questions, but I'll
Yeah,
you try to check in the chat.
I'll just unmute. Is
Yeah,
that
okay.
okay?
Yeah, you can.
Okay, cool.
Uh, so right, so like the idea is that the function is not convex, like the rank function is not convex. So here's an example of that. Um, so for example, like if you take the diagonal, just take the diagonal matrix 1 half, 1 half, and zero everywhere else. So this matrix has rank 2, right? But that is a convex combination of these two other matrices, right? Um, and each of the other two matrices have rank 1, right? And if you just check like if you just check the definition of convexity, if the function were convex, then you would have like the rank of this convex combination of the two matrices would be less or equal to 1 half the rank of one matrix plus 1 half the rank of the other matrix, right? But it's not true that what like two is not less or equal to 1, right? So like if you do 1 half, 1 half, you get 1. So that's one means that the rank is not a convex function. Uh, and again, the idea is that there's kind of like a package of convexity that is kind of like useful to solve optimization problems. So even if the original problem was not convex to begin with, as a first like starting point, it's useful to convexify it. Like try to kind of like turn it into some sort of like convex problem, which is what I'm about to tell you now. Like how we turn what's kind of like the convex replacement for the rect. But it's like the a convex function that, in a sense, is like as close as possible to the rank of a matrix. And that's something that's called like the nuclear norm of the matrix or something like that. Okay. Is that making sense so far? So good questions. Okay, so this is actually like the terminology for this type of thing is like relaxing the problem. So you can like change the problem into something relaxation in the sense like you're turning it easier, like in some way, right? I think the example I had told you about like that happens a lot in linear programming. If you have taken that class, linear optimization is that when you're trying to solve an integer program problem, right, where the solutions are integer values, and then you replace that by the kind of like the convex hull or something like that of like the lattice of like that contains that integer points. So idea being that if you do that, like you have changed the problem to something easier to solve. So here's like I mean, this is kind of like an elegant way to do it, to think about it. So you have like the heaviside function, which you probably have heard of before. So it's just like a function, right? Like it's zero for like negative value for x is zero, and it's one for positive values of x. So it becomes one if you give it like a positive input, right? Um, so then like
How do we create this function,
well,
the Heaviside function?
it's just like I mean, it depends on what you mean. How do you create it in the sense? I mean, it's just like a
Oh, it's just like a definition.
right. It's just like an activation function, right? It like activates. It's like if you think about it as a signal, it's off for negative values or zero, right? And you turn it on if you know if you feed something positive to it. But as a function,
Yeah.
it's not too complicated like from a mathematical perspective because it's just like discontinuous at one point, but and then it's constant. It's really just two constant functions, right? Like but with like this discontinuity. So but yeah,
Okay, yeah.
but yeah, kind of like the reason why it's useful, if you ever do like Laplace transform or Fourier transforms and things like that, it's just because yeah, you can think about it as a like some sort of like activation function, and it's also related to the Dirac function because it's derivative in some sense it's like the Dirac function. Uh, the delta Dirac. But yeah, like this is like kind of like just think about it as it gets activated if the input is a positive number. Okay. And
Hmm.
from that
Okay.
perspective, then what's nice about it is that it allows you to rewrite the rank of a matrix in kind of like a somewhat elegant way, um, because so let's see if I can explain what this is. So remember that when you have a matrix, you have the singular values, right? So if you had a matrix A, you had the singular values, right? And the singular values were always non-negative, right? So in fact, the rank of a matrix, what is the rank of a matrix? The rank of a matrix is the number of positive singular values, right? So the rank of A was the number of strictly positive singular values, right? But one way to think about it, maybe, sorry, just to put like an intermediate step here. One way to think about the rank is kind of like, oh, you have a one for each positive singular value, right? Like, and then the rank is just one plus one plus one plus one plus one. How many times one? How many times do you add ones? As many singular values, positive singular values that you have. So one way to think about the rank is as a sum of like you add a bunch of ones when for over all the singular values that are strictly positive, right? This notation isn't the best, but yes, it's positive. Oh, right. Sorry, yeah, like I don't know. Yes. Like here, like right, like because the others like would be zero by default, right? Like, yeah, exactly. But so what I'm trying to say is like the rank, one way to think about the rank is as a sum of ones, one for each singular positive singular value. But if you feed a positive singular value to the Heaviside matrix, that's Heaviside function, that's precisely what you would get at one. And then you would get a zero. Otherwise, if the singular value happens to be like zero. So a nice way to think about the rank of a matrix, right? A nice way to think about the rank of a matrix is just as which is like the advantage that it has is like what you were just saying, that actually you don't have to kind of restrict the value of the sum, right? Like you can just go like over all values. It's just kind of like a sum of Heaviside functions, right? Evaluated at the singular values of the matrix. Is that okay? Is that making sense? Kind of like the idea.
Yeah. Could you explain the convex thing below? Like why
Oh, so
that
what I
makes
was,
sense?
well, that's what I was going to say next. So if you think of the rank, okay, so what I was saying is that the rank function is not convex. In part, it's also, now that you think about it, it's not convex because the Heaviside function is not convex. It's also like kind of like related to the same issue that the Heaviside function is not convex. So one way to kind of like convexify the rank is instead to convexify the Heaviside function, and you try to find like a convex version of the Heaviside function. That's one way to, that's what like the motivation for doing it this way that of what I'm saying. So you're trying to find a function that's convex that kind of like agrees as much as possible with the Heaviside function. Okay. Um,
What property of the Heaviside function makes it not convex?
well, so the idea, like, where, like, let's see, like, it would be kind of, let's, if you have like a, where, well, how should I say it? Like, because I'm trying to write a linear combination, you could have, let's see if I can work it out here. So, uh, let's say you had, so let's say you have 0 here, you have 1 here, right? And then you have 1/3, right? The number 1/3, okay? So the Heaviside function at 1/3 should be 1, right? But let's see if this is going to work. Right, but at the same time, the number 1/3 is a convex combination of 0 and 1. Okay, so 1/3, I mean, but 1/3 is, okay, how should I do? Let's do this. It's 2/3 times 0. Okay, this sounds silly, plus, okay, I'm doing it from like top of my head, so hopefully this one works. Plus 1/3 times 1, right? We're okay with this equation, right? Like it's kind of like tautological, it's kind of like circular, but if you think about it this way, 2/3 and 1/3 are kind of like the weights in the convex combination. So this is kind of like one is t and the other is 1 minus t. That's kind of what I'm trying to set it up this way. So this is kind of like the t and the other one is like the 1 minus t in the convex combination. So if the Heaviside function were convex, right? If the Heaviside function were convex, then what you would have is that Heaviside of 1/3, right? Which is Heaviside of this convex combination, 2/3 times 0 plus 1/3 times 1 would be less or equal to, right? Sorry, just to go back for a moment, this is where I had written the definition of convexity, right? The convexity was, where do I have it? Here it was. Like the definition of convexity was this, that if you have like a convex combination of 2 points, then the value of the function at that convex combination is less or equal to the convex combination of the outputs. That's one way to think about it. And so what happens if I do this? Hopefully it's not a complete mess. So you get 2/3 times h of 0, right? Plus 1/3 times h of 1, right? But what is h of 0? H of 0 is 0, right? And h of 1 is 1. So this is just 1/3, right? But this is supposed to be 1, right? And it's not true that 1 is less or equal to 1/3. Okay, is that making sense?
Okay, yeah, that makes sense.
And actually, I'm glad that you asked me this because kind of it skips the proof of how you should convexify it, because now you see the issue is actually between this interval 0, 1. That is actually where like the convexity can kind of like create problems, like because you have like a point in the interval 0, 1, and you can always write it as a convex combination trivially from of 0 and 1. So that convexification, I mean, that's actually is essentially the same calculation that I was doing here, but the convexification of the Heaviside function, it's just that. So it's just like basically it's like kind of like a piecewise linear function, right? Like here, like is the identity on this, like it's kind of like this part is y equals x, and that one is easy to check that makes it convex. Okay. And so the idea is to replace, actually, yeah, just to go back. So the idea is that the rank, right, like the rank, which was these, I mean, just like seems plausible to replace it with this, convexification, like of the Heaviside function. Again, like I didn't give a name for this one, but let's call this f of x, this function. So this is a function y equals f of x. Okay. And that, at a more practical level, what that's saying is that you're replacing the ones, right, like over all the positive singular values, with just the sum of the singular value, which with the sum of all the positive singular values. So this is a function that I want to work with, like the sum of all the positive singular values. It's kind of like an L1 norm. I'm actually going to say something about those norms in a moment. It's some sort of like norm, and this is called the spectral. No, it's called the nuclear norm. I mean, there's a spectral one that I have to tell you, but this is called the nuclear norm of the matrix. So, oh, okay, perfect. I haven't written anymore, but now we're getting on the right track. So maybe let me give it as a definition. If you have a matrix, you have a matrix A, then its nuclear norm A star is defined as what you just saw. It's basically the sum of all the positive singular values. I mean, obviously, if the singular value is 0, it doesn't count. So like you can just say it's like the sum of all the singular values if you prefer, right? Like it doesn't make any difference if you add like the ones that are 0. So you might as well just add up.
Why is it called nuclear norm and not just
Uh,
like the norm?
that actually, uh, I'm not sure what the origin for the word nuclear is in this context. So
Hmm.
yeah, I'll leave you hanging on that one because I'm not 100% certain of why they call it the nuclear norm in this case. Do you have an idea? Oh, the thing is like okay, so there's kind of like this, you can like look at all the, what I was doing here is that if you had, you know if you had it, what I was trying to show here is that if you had any convex function, right? It has to be less or equal to x. So any convex function is always less or equal to the identity. And then you kind of like the convexification is kind of like the max, like the largest possible convex function that's underneath the function you start with. So there's kind of like a technical definition of what the convexification of a function is. So of all the convex functions that are underneath the function, you take kind of like the supremum, like like the maximum possible. So that's what So that's why you kind of like take it as like the identity, because that's kind of like they always have to be underneath the graph of the identity function, right? And then you just like the largest possible, that makes it the closest one. You see, to the Heaviside function because that's the max. You know, you're saying that any convex function, right, on 0, 1 has to be always less or equal to x. So like the largest, like the one that would be closest to the graph of the Heaviside one would be the identity. Sorry, oh, well, I'm doing it for the interval between 0 and 1, right? Yeah. Because then like the things that before 0, like the function was always constant, right? So I'm just kind of like fixing the non-convexity that arises on the unit interval, right? Yeah, but right, because like otherwise, you're looking for a function like before 0, you're looking for a convex function that's always less or equal to 0. But it just takes 0, right? Like just take the constant function 0. That's but there's like a technical. I mean, there's like it's kind of like real analysis. There's a thing about the primum when you take kind of like a primum of all the possible complex functions underneath the graph, and yeah, that has a name is complexification. And it's two other complex. Um, Okay, so this is well, but again, like this is kind of like interesting because now and in fact you can kind of like prove that this is a complex function and everything. I mean, I kind of like I'm doing it more as like a motivation of where to get complex, but you can kind of like check that I'm interested in this convex. And what's actually also interesting is that it is. I mean, in fact, one way to prove that it is convex is just using the fact that it's like a norm. Like all norms are convex functions. So I'll just kind of like give you like the definition of a norm in the case of a vector space that just kind of like generalizes the Euclidean norm. So what is a norm on a vector space? A norm on a vector space. Again, that generalizes it generalizes the Euclidean norm of a vector. I'll put EUC for Euclid, right? Like the Euclidean norm of a vector, which was just a sum, the square root of the sums of the squares, right? Like Pythagoras theorem. Well, this looks too ugly. I'll write v1 squared plus v2 squared.
Would it be like the sum of the basis vectors?
Well, it is it's not the sum of the basis vectors because it depends on what you mean by that. You do want the norm to give you a number, right?
Or
So
like the sum of the norms of the basis
oh
vectors?
that one it is there's one that's kind of like related to that, which is called the L1 norm. So I'm going to give you some examples in a moment. But yeah, one of those is kind of like along those lines. But like the definition of a norm, which I'm about to write, is kind of like the most general one that usually is used. But yeah, like this one is closer to what you're saying, like this L1 norm. But there are other norms like L, which I'm going to write in a moment.
Hmm.
But so the idea is like the norm, like basically it has three properties. One is that I'm going to write it for like kind of like assuming that it were like a matrix, but it kind of like works in general. The norm of a matrix is 0, the number 0. Sorry, I should say that the norm is a real number. So it's not negative actually. No, the norm is always greater or equal to 0 for any matrix. And again, it could also you can also do this for vectors or like tensors or whatever. Like like the formula would be like the conditions are the same. So I'll just put matrix, vectors, tensors, etc. It can be defined on any vector space. So you want that the norm is always greater or equal to 0. That if the norm is 0, then the vector is or the matrix or the tensor is exactly 0. So the only one that has like 0 norm is the 0 matrix, the 0 vector, etc. So this is like the first property. Exactly, only when A equals 0. When I write here 0, I mean 0 vector, 0 matrix, 0 tensor. So 0 matrix, the zero vector, or the zero tensor, depending on what you're working with. Okay. And then the two properties that are a bit more interesting that makes it nice is the scaling property. So if you rescale the vector, the matrix by or the tensor by a scalar, you can take it out in absolute value, the scaling. So that's why in Calc 3, if you took Calc, well, you did take Calc 3, I think most of you, right? Like already. So like you would like remember like the norm of the vector, like that's why the notation is similar to absolute value because it's kind of like behaves in a similar way. So it's kind of like a generalization of absolute value. That's maybe the better way to explain this. So here T is a scalar. And the last one, which is the famous triangle inequality, which is that the norm of a sum is equal to the sum of the norms. Okay. I'll put this one in a different color because that's kind of what makes the norm like a very useful concept to work with. Well, like, let's just give you some examples in Rn, like for vectors. So some examples include the L1 norm, which is really, it's kind of like similar to this one with the with the sum of the singular values. So here's like some examples on Rn. So if you had a vector, right? If you have a vector with n entries, so one, well, the well, like the L2 norm would be the one that you know, but one is called the L1 norm, which is the L, and usually you just write like a one as a subscript. So it's just the sum of the absolute values of the entries on the right. Okay. Which is easy to check that it's a norm because it basically inherits the properties of absolute value. So the triangle inequality, which is kind of like usually the most important one to check, like it is a consequence of the fact that the triangle inequality is satisfied, entry by entry, for the absolute value. I mean, the absolute value satisfies the triangle inequality. Then, uh, then you have the LP norms, which is greater than one, which are very important in analysis and probability theory and many other places. Um, Here P is a positive number greater than one, which is that the LP norm of a vector is the pth root. Okay, so let's see. You kind of like do it's a generalization of the Pythagoras theorem, right? If p equals 2, that is basically Pythagoras, the Pythagoras theorem, like of the norms, right? So this generalizes the one that you know for p equals 2. So generalizes the one that you know. And there's also like the L infinity norm, which is the maximum of the entries of the vector in absolute value. So the L infinity norm, those are kind of like the three most important families of vectors on our end of like norms they usually run into. So the other one is called the L infinity norm, which is just that the L infinity norm of a vector. You you look at the entries, you select the largest one in absolute value, and that's its L infinity norm, basically.
Limit of L when it can be, would it be
Uh, yeah, I'm pretty sure that's why the notation is like that, but I would have to double check the, like the proof. But yeah, like, I mean, it's suggestive of that, right? Like uh, you might be, yeah, you might need to be careful of how you do it though. But yeah, like, I mean, you kind of like do think of it as being at the end of the LP norms, right? Um, I mean, there is definitely an inequality, right? Like there's kind of like a clear inequality because each of these entries is therefore equal to the max, right? So wait, you can replace every entry, right? You can replace all of these entries with the maximum entry, right? Well, I mean, I guess you have to check that this function is kind of like, like preserves inequalities or whatever, right? Like, so maybe you have to be careful about that. But, like if you kind of like put the, okay, and then okay, now this becomes like a constant, right? Like, so you take out the you get n times the L infinity norm to the p to the 1 over p, right? Like the 1 over p's cancel, so that gives you the infinity norm times n to the 1 over p, right? And I guess this is kind of like one of these calculus as p goes to infinity, right? Like you get n to the 0, which is 1, right? So so for any p, these like LP norms are less or equal to the L infinity norm, and as p goes to as p goes to infinity, then it does like approach it, right? That's what it's called, like when we put them you probably remember it. Right? Like when you take all these limits of sequences. So right. So like what that means is that so and then for any p greater than one, and then take limits, and then that gets by the okay. So and then for matrices, okay, so for matrices, there's similar norms. So one is called the Frobenius norm, which is actually the one that we were using all this time. So just to also give you like some examples for matrices. So this is called matrix norms, right? The one is called the Frobenius norm. This is maybe I should put the name of it here. Which is okay, so there are a couple of ways to think about it. One is it's just basically Pythagoras theorem for all the entries of the matrix. So it is like the sum over I and j of aij squared to the 1/2. So it's kind of like Pythagoras theorem. Um, but it's also we actually do this for this is also like it's kind of like ends up like being, I mean, there are other ways to write this down, right? Like this is also the square root. This was also the square root of the trace of A transpose with A. And that also was the same as the sum as the square root of the sums of the squares of the singular values. So this is also, so there are many characters. What I'm trying to say is that there are many characterizations of the Frobenius norm, which is why it makes it like an interesting norm as well. Well, like here, like sigma I squared. I'm pretty sure we have talked about this right? The sum of the squares of the singular values. That's where the NPV comes in. If you do the NPV, if you use the formula in terms of the trace, then you apply the NPV composition to A and A transpose, you just end up getting like the diagonal square or something like that. And you take the trace of the diagonal square, and that is simply the sum of the squares of the singular values.
Professor,
Yeah.
I didn't know the trace of like A transpose A was the singular values added up squared.
No, we did that like it was more like
I thought it was you had to find the
well,
singular values or eigenvalues from it.
if you do the singular value decomposition, if you write U equals A equals U times sigma times V transpose, then
Yeah.
A transpose would be what? It was V times sigma transpose.
Oh, wait, I remember this homework
Yeah,
problem.
yeah, yeah. Well,
Yeah, I
actually,
remember this.
I may have even done it in class, but yeah, once you do A transpose A, right? I mean,
Yeah.
yeah, like kind of like the U's, like and the V's cancel, like you get what? You get
Yeah.
V something like that. Yeah, that because the U's and V's are orthogonal matrices, so this kind of like gives you the identity, and then because it's a trace, you can move the factors around, so you get kind of like you get V sigma squared V transpose, and then yeah, when you take traces, you can kind of like do a cyclic permutation of the factors, and then that's how you get rid of the V transpose, and that's how you got like the
Yeah.
yeah.
Yeah, because literally that's like the definition of the trace is the middle matrix,
Uh,
right?
Correct. It's kind of like well, it's not the definition, but yeah, like the cyclic property is what you use. But yeah, like it's well, if you think about it in the tensor diagram notation, it was easy to see that you could just move around the wires. That's actually we had
Oh,
in class. But anyways, so it's
okay, that makes sense though.
the point
Yeah.
that it has like many useful interpretations, and so that's kind of what's nice about it. And then there is another one, which is interesting also, which is called the operator norm. So the operator norm of the matrix, or the spectral norm. I'll just maybe call it the spectral norm. Oh, first, before I write that down, the other one is like this nuclear norm that we just talked about. So another one would be the nuclear norm of the matrix. Which would be the sum of these singular values. So you see, this is kind of like similar to the L1 norm. It's just that the singular values are always positive, so that's why the absolute value is not needed. But if you want to make it closer to kind of like the L1 norm of a vector, it's kind of like if you kind of like put all the singular values as a vector of singular values, this would be the L1 norm of that vector of singular values. So this is like the L1 norm. It would be the L1 norm of the vector of singular values. So sigma would be here. Sigma 1, sigma 2, up to sigma rank. And then there's a bunch of zeros, right? Kind of like put all the singular values as the entries of a vector of singular values. So in a sense, the nuclear norm is kind of like the L1 version of the norm of a vector, like from that perspective. It's kind of like a similar. And the other one, like this operator norm or spectral norm, which if I have time, I'll get to in a moment because there's still some other things that I want to mention about this matrix completion problem. But the other one is this spectral norm, which is Um, Well, I'll write SP for spectral. Um, again, there are other ways to characterize it, but so let's think about what this is saying. Like, and I still have to say a little bit more here, but A is a matrix, right? So if you multiply A with a vector, you get a vector, right? And then you multiply it with another vector to get a number. So this is going to be a number. Like if you prefer, you can write this as V1 dot A V2 if that makes it kind of like look a bit easier. Of course, V1 and V2 have the correct so that this makes sense. So all that I'm saying is that you have you want to kind of like extract a number out of a matrix, and it's kind of like a contraction. If you think about it, in the tensor diagram notation, which we haven't used in a while, the matrix had two legs, right? And you kind of like you can feed two vectors into it to contract it, and that's kind of like what this is representing. Okay. Well, I won't write the indices names because I don't like. I would have to be more careful which one is which, But all that I'm saying is that one of these would be V1, and the other one would be V2, and that's how you get a number. Okay, so that's a number. You take its absolute value, right? That value depends on which vectors you use. So you take the max of all the possible vectors you could use of each of them with norm less or equal to one. So it's kind of like the unit, kind of like on the unit square. So the maximum is being taken over all those vectors whose Euclidean norm is less or equal to one.
So wouldn't you always want like your vectors to be like one? Because if it's less than one, it would just like shrink the value.
Well, it can uh you have sometimes it's how should I say it? Like it can
Because
like
it's always going to be positive, right? Like all the values of the
well
matrix.
I mean it can be still achieved. I think in this case it is achieved at the thing is like how should I say it? How should I say it? Like it's like it's a max over two quantities, right? Like like because you're finding all the vectors, like v1 has to have norm less or equal to 1, and v2 has to have norm less or equal to 1, right? So it's not super obvious at the moment that that, but since you have to play with both of their, let's see, you can always write, well, I guess in this case, yeah, because you can always write a vector times uh, the proof that this is kind of like you can kind of like do an SVT decomposition, but no, I think like you have to be more careful about that because it's just like I'm sure like you could kind of like think about it for like a concrete matrix because it's a kind of like a max over two. It has two conditions, so maybe like it could be possible. It's kind of like okay, the analog of this, what you're saying is equivalent to saying that if you had a function of two variables, right? That if you like, this is kind of like analogous to the unit square, like the norms. So because like each of like the norm is between 0 and 1. And like the max of a function, like in general, wouldn't happen necessarily at one of the edges of the unit square. That's kind of like similar to what's going on here. It's a little bit different because this is like it's a very particular type of function. So it could be the case that in this case it does get achieved at one of the edges, but it's still better to just like leave it as a you know like with the less or equal to, because for other cases when you generalize in there you do need it like with less or equal to, so that's kind of like the idea.
Yeah.
But
Yeah. But if the matrix is always positive, like
well
then the max on things should just be one.
Oh,
right?
well, but like the matrix is not necessarily always right. Like the matrix here can be anything, right?
If
So
the matrix has negative values, then obviously, yeah, it would change things.
but also like the thing is like even if the matrix is always positive, right? Even if the matrix were always positive, like like the vectors, like they both have positive and non-negative entries, right? And you could have something, um, you could have like one entry being negative and the other one also has like an entry that's negative. So, it's a little bit more complicated, like the sign game, because, you see, like, that's what I'm trying to say. It's not as clear as it may seem, like, whether you can replace the less or equal to with equals. So it's better
It'd
to
be
think.
less than 0.
Well, no, this is always be like, in the norms are always non-negative numbers, right? But because
Okay.
the fact that the Euclidean norm is between 0 and 1, it's kind of like, that doesn't say that the entries of the vectors, like the entries of the vectors are kind of like inside the unit disk. Like, for example, if you think about it in 2 dimensions, like then like
Uh,
that would, or like on the unit interval, that would actually be.
yeah.
So that's all that I'm saying. Like, it's a little bit more tricky because of the game of signs. Since like the entries can be both positive, negative, not only on the matrix side but also on the vector side. And then when you do generalize it to tensors and other things, it's actually there, like definitely you do need the less or equal to. Like on the matrix, I'm not like, I have to kind of like double check that, but for other things, like you do need the that to keep it as less or equal to. What I was going to say is that the reason why this is called the spectral norm is that it also coincides with the largest singular value of the matrix, which is kind of like cool. So that you do need to use the SVD decomposition to prove it, but this in spectral norm is the sigma 1. Remember, like sigma 1 was always the largest singular value of the matrix, so.
So in other words, it kind of strips like a matrix down to just show it's like the value that it's like most weighted in the
Right, right,
matrix.
right. Like it's kind of like the direction is right. Like the largest singular value is kind of like the direction in space where the most stretching or whatever is taking place, right? So it's or the most
Yeah.
important direction. So yeah, it's kind of like similar to this L infinity norm of, it's kind of like a max of sorts. It's like the max of the singular right? Like another way to think about it is kind of like the max of all the singular values.
Yeah.
So in that sense, it's kind of like the L infinity norm. If you arrange all the singular values as a vector, it would be the L infinity norm of that. So in the case of a matrix, there's a lot of like interesting ways to kind of like refer to these norms. That's what makes them like equal things to work with.
Makes sense.
No, okay. So just maybe, I mean, this was a good, I think this is a useful thing to just know that there are like all these matrix norms and things like that. But maybe like was a bit of a detour to what I was telling you. So going back to the matrix completion problem. So that's the idea is that, as I was saying, the original matrix completion problem is that you were trying to minimize the rank of a matrix, right? With the condition that on the sampled entries, like on the observed entries, like the matrix would agree with the one that you already have. But because the rank behaves poorly, you change the problem, different problem where you want to minimize the the nuclear norm of the matrix still under this condition of like agreement with the sampled entries. So kind of like the new optimization problem that you have to try to solve. Because in a sense, it's more doable. That's kind of like the idea. is that you're trying to find the minimum. Oh, let me write it like this. You're trying to find a matrix B, find B such that on the sampled entries, it agrees with the matrix A that you started with. So that this means that the entries agree with those of A that were sampled, with the ones from A that were sampled. And again, of all those matrices you that would have that condition, right, which like there are infinitely many, you just try to locate the one whose nuclear norm would be as as low as possible. And is meaningless. Of course, like, when you write an optimization problem, there's no guarantee. I mean, you can just write whatever optimization problem you want in the world. That doesn't guarantee that there would be a mean, right? Like, so you have to, like, put other conditions to kind of like see whether like this is like a realistic thing to last, right? Like, but that's kind of like a more like a reasonable goal, just because again, this nuclear norm is a convex function. That was making, and then again, there's a lot of machinery in convex analysis to try to find the minimum of a convex function. One of the nice things, I may have said this before, one of the nice things of a convex function is like, for example, local mean is automatically a global mean. So this is the type of things that you appreciate about like a convex function. No, something again, like because definitely I won't have time to kind of like put all the ideas here, so I'll finish writing them up on the PDF, and someone wants to kind of like find more reference. But at least something that is useful to mention as well, more like which is more related to the problem of the matrix completion per se, is that you also have to be realistic, as in the sense that you wouldn't necessarily expect this to work for any matrix that you start with. So here's an example of what could go wrong. And then I'll tell you about the coherence, which is like a useful idea for this type of problems. So what could go wrong? So let's say the matrix that you had to begin with, well, like was just 0, 0, 0, 0, 0, 0, 1. There's just going to be one in the first row and last column, and zeros everywhere else. Okay, so this matrix is a bunch of zeros, right? Except a one, right? That has it in the top right corner. So this is the matrix of rank one, right? So this is like the matrix of rank one. Right? But if you thought about it kind of like probabilistically, right? Like you are trying to like, sample the matrix, right? Unless you happen to use as one of your sample entries, like the one in the top right corner, you would only see 0 after 0 after 0 after 0. It doesn't give you much of a chance to tell, like, like that the matrix had rank one, for example, right? So this is, in fact, like if you write it using the tensor product notation, let's say that this matrix, like, I mean, just to make it like easier, let's say that this were like a square matrix, not that you have to, not that it needs to be square, but just to kind of like make it easier for me to kind of like play with the indices. This, in terms of the tensor product, this matrix is kind of like E1 tensor En, where like E1 and En are the basis, the canonical basis vectors, right? So, so what I'm saying is that in this case, you wouldn't expect the whatever algorithm or whatever matrix completion to try to solve, you would do to work very well, because you have to kind of like be very lucky, to just happen to run to the end, then you need to running to kind of like complete. So essentially what's happening here is that if you look at the, you know, if you look at the singular at the SVD decomposition of this matrix, right? This the kind of like the singular vectors are, you know, like the singular vectors were like the column vectors that make the U and the V. You know, they are basically the canonical basis, like they're made out of like the canonical base. So what you could like for, you know, like a chance for like this completion to work is kind of like for the singular vectors of the SVD decomposition to be all like kind of like scrambled all over the place with the canonical basic vectors, kind of like not to be what's the word concentrated in a particular direction to space. So essentially the issue here is that and you would like the matrix and you would want the and in the SVD decomposition you would want the vectors that make up the matrix U and B to kind of like be uncorrelated in some way with the canonical basis. So and for the SVD decomposition, you would want the vectors which make up U and V to be uncorrelated to the basis vectors as much as possible. The canonical basis vectors. Because again, the idea is that kind of like the basis vectors pick up this axis in on our end. So if kind of like the matrix is constructed out of this axis, unless you happen to sample specifically in those directions, then you're kind of like screwed. So like you want kind of like more kind of like a random distribution of like the singular vectors to be kind of like being like constructed like in an, you know, uniform way from like the basic vectors in some way. And that is actually, there's kind of like a more precise way to define that, which is called like a coherence of a matrix. Maybe it's like a good place to, I mean, I'll tell you what the coherence is now, but it's a good place to kind of wrap up, and then I'll kind of like just fill in the blanks of what that later to kind of like prove the theorems. But basically, just kind of like to give you in a nutshell what's going to happen is that the coherence is kind of like going to measure like how much the singular vectors are related to the canonical basis. So a matrix of large coherence means it's kind of like one like this, where kind of like the singular vectors are very close to being the canonical basis. And so a matrix is very incoherent if that does not happen. So those are kind of like the ones that you think of as being truly random in some way. So the idea is that if you have a matrix that's incoherent, then with high probability you can find a minimum, you know, you can kind of reconstruct the matrix with the matrix completion. So the idea, I mean, of course, has to be, there's a lot of technicalities going on, but what I'm trying to say is that the coherence is what you need to like have a chance for this to work out. And then you can extend this to tensors. So the idea is that you can kind of like define an analog of the nuclear norm for tensors, which I'll write down in the PDF so that you can read what the analog is. So you can write down an analog of a nuclear norm for tensors. So that, and then you have an analog of also what's the coherence of a tensor. And once you have those two things in place, you can kind of like do something similar to have like a tensor completion, a problem that can be solved. So this is an extension of like in signal analysis, kind of like like, like the recovery of like a signal, like in, with the big matrices and um, but yeah, just to kind of like give you a motivation first of what the coherence is. What is the coherence of a vector subspace? No, it's good to start with a picture so that you can kind of like convince yourself of what should happen. So imagine that you are on R2, right? You have on R2, you have the canonical basis, right? This is E1 and E2. And let's say that on R2, you're trying to find a subspace which is kind of like uncorrelated or not like in the direction of any of the canonical bases. So for example, if you chose the x-axis, that is a bad choice, right? Because it's literally pointing in the direction of the E1. If you choose like the y-axis, that's also pointing in the direction of the vector E2. Almost by symmetry, we would think that the best possible choice is the one that combines E1 and E2 the most, which would be, for example, the line y equals x, right? So if you think about the subspace, you know, this is like a vector subspace of R2, right? And in a sense, that's kind of like I mean, it's kind of like the most symmetric direction between X, like the x-axis and the y-axis, right? So it kind of has like 50-50, like for each of the canonical base right there. So what is one way to make this precise? So one way to make this precise is that if you project the canonical basis onto the subspace, right? If you project, okay, so how can you do this projection? Well, they actually have kind of like the same projection, roughly in this case, right? If you kind of like project the E1 and E2 onto the subspace, right? Then the projected vector has kind of like it's a small the path. Okay, so that's kind of like the idea that this projection is not too large in some sense. Okay, because again, if you kind of like have chosen like the subspace to be in the direction of one of the canonical bases, then that at least one of the projections would be very large, right? Because one of the vectors would be its own projection. So kind of like the coherence is just kind of like going to measure. You have like the canonical basis, you project each of the vectors of the canonical base onto the subspace, and what you want is for those the lengths of the projections to not be too large. To try to make them as small as possible. So here's like the coherence, and I'll finish with this definition, and that will be the last thing I write. So you have the coherence of a vector subspace. I'll call this vector subspace W of Rn. So I'll say that the dimension of W is R because I'm thinking kind of like as the rank. So it's kind of like in this problem of the matrix completion, W would be kind of like the column space or the row space of the matrices in the SVD decomposition. Okay, so W here, like the dimension of W would be R. And for the matrix completion, W would be like, for example, like the column space of U and the column space of V in the SVD decomposition. Okay, so the idea is that the coherence Let me see how people write it down. I just forgot that notation to use. Yeah. Well, I'll just call it the coherence of W is the following. So basically, again, you take each of the canonical bases, right? And you project each of the canonical basis vectors onto W, right? It's norm squared. I mean, the square norm is just kind of like easier to work with, I guess. So you take the norm squared. Okay, you look at how bad can this get, so you would look at like what's the maximum of all the, you project for each of the canonical basic vectors, you look at its length squared, you look at the max of that to see how bad can it get. And then that is basically what the coherence is, like you're just measuring how large the shadows are, like the projections, and then you just put like a rescaling factor, so that kind of like a normalization standard. So you multiply by n divided by r. Okay. Let me just check that. And I wrote it in the right order. So yeah, that's kind of like the factor in front is kind of like a normalization. So because the idea is that, for example, say if one of the like a projection can only decrease the length of a vector if it does if that makes sense, right? So the projection of EI, the most it can have one of these vectors, the length of the projection vector squared, the most it can be is 1, right? So the largest this could ever be is exactly 1, precisely when one of the vectors happens to be in the subspace W, right? So kind of like the worst case scenario for us, because we want kind of like the singular vectors to be scrambled all over the place. So for us, large coherence is bad. That's how we're thinking about it. So large coherence is bad for us. And so, for example, the worst it could get is like if one of the max, like, again, the projection, the worst it happens, worst occurs when one of the canonical bases, one of the EIs belongs to the vector subspace W, because in that case, the projection vector is itself, since then the projection of EI would be EI, and its length square would be 1, right? So and if that's 1, that means that the coherence for sure the most it can be is n divided by r. So the coherence is always bounded by above by n divided by r. So coherence and the smallest value you can take is 1. And also it's bounded below by 1. That happens because kind of like it's similar to this case where, like with the line, if you think about it, like kind of like the most scramble it could happen is kind of like if all the entries of the vector are equally likely, like if the projection, when you project the one of the canonical vectors, or if all of the canonical vectors are kind of like all the coefficients are kind of like uniformly distributed among the subspace. So the idea, and maybe just to give you like and just to be a bit more concrete, basically what I'm saying is that if when you project a vector, right, you can always express it as a linear combination of an orthonormal basis of the subspace, right? So it would be kind of like a sum from I to R of of a linear combination of the of an orthonormal basis of W. And then like the length square is kind of Pythagoras theorem as before, right? If the basis is orthonormal, you know. You get that, and kind of like the most random, like kind of like almost like a uniform, like scrambling of the vector would be where like all the coefficients are of the same value, right? And like you know, kind of like uniformly, kind of like that all the directions are when you project are counted the same. So like it's the most it could be would be this would be kind of like if all CIs are the same. This would be kind of like C1 squared times R. Okay, so that's why you start seeing why you divide by R, so that this R kind of like cancels this R, and then each of the C1 squares, like the most they could be, you know, again, since if you would be 1/n times R, and that's again like by Pythagoras here, because again, like it is in a vector space of dimension n, and you can like extend this vector, this basis of W to a basis to the entire sub, the entire R, and then if it's completely random, then kind of like each of the coefficient squares would have like 1/n of the total length of the vector. So that's where this is coming from. And in that case, the coherence for that vector would be, and so again, it's kind of like being a bit sloppy, but that's kind of like the idea behind it would be n/r times r/n, which would give you 1. And that is more or less kind of like the best case scenario where it's kind of like all completely random. And that's where like you get like one of the lower bound. So you cannot go on below 1. That's what I'm trying to say. And the idea is that, which again, I'll kind of like write this down more precisely on the notes, but the idea is that if the matrix has low coherence, then with high probability, you can kind of like recover, like solve this problem, like exactly. So you can recover with high probability all the entries exactly. And then there are other versions where like it's not exactly, but with some errors or noise. But the idea is that if the coherence is low, then one can recover with high probability the matrix A. Okay. And that's kind of like the idea. And again, I'll fill out some of the details on the notes so that you can kind of like read more about it if you are curious. But I think this is a good place to end because it's, you know, I mean, it has been all like many different topics, you know, but hopefully you kind of like have seen like a flavor of like all the different directions that you could go into this stuff, right? Like, so, which I think ultimately was more like my goal, where like it's more like, oh, if you ever open a paper now, maybe now like 70% of the terms, right? Instead of like 10% of the terms, like now makes sense. Like, you know, if you open like a paper on tensors or like even some of this stuff of matrices and things like that. But yeah, I'll try to give you some office hours in case someone, you know, wants to ask me anything about like the remaining problems, which again, you can upload kind of like around December 19 if you're still not done with them, because I wouldn't put grades anywhere anytime before that. I'll try to kind of like keep grading them now that I don't have to keep preparing the classes. I have more time to kind of like get back to the grading. And so I'll try to grade that like maybe over the weekend so that you have a little bit more feedback in case you want to ask me, you know, something about that specifically during the reading days or like during the exam period. And if not, just in case, like if there was not something specific that, you know, you wanted more explanations of, like you can also stop by if you want to ask me, if it's, even if it's not like a specific problem, but if maybe if there was something that you wanted more references because you wanted to learn more about, I can also point you in that direction. I have like 100, like I don't know, I have like 500 pages. I ended up printing them all because I went back old school. Like I cannot read more from the iPad. So I ended up printing a bunch of stuff. So like I have so many papers that I could recommend you if you want kind of like to get more like into the nitty gritty of how some of these things work. But yeah, just end here and then like I still have office hours like in 10 minutes if someone wants to ask me something. Okay, so oh bye. I'll see you around. Yeah.
Thank you so much for the semester. It was a
Oh,
great class.
I'm glad you
Had a
enjoyed
great
it. Yeah.
time.
Are
I'll
you
be,
you're taking topological data analysis, I imagine, right?
I want to. I don't know exactly yet because I'll have to go over like 21 credits to do it.
Oh,
So
I mean, you are always welcome to, just sit on, like, what's the name that people give to that? Like, just sit on the course their way.
I don't know. Is it like, can you hear me? Sorry.
I can hear
Hello?
you. Okay, I can
Oh,
hear you.
it's cutting out. It's cutting out. Oh yeah. So I was thinking um like worst case scenarios I could just like come to the lectures of the course
Yeah, yeah.
because I don't think they're gonna let me go
I'll
over
also
20
record them
credits.
as well. Yeah,
And
yeah,
you can email me like the times and stuff.
yeah, yeah, yeah. I mean,
Yeah, and maybe you can let me in the
I will
Canvas.
definitely add you on the Canvas side. Yeah, but you can keep me posted. Yeah, yeah, yeah. If you need that. So yeah.
Yeah. Cause so like maybe not on my transcript, but obviously
Right,
I would
right.
still come to the lectures
Yeah,
because
yeah, yeah.
I want the continuation or whatever
Well, I
this
mean,
is.
you were the one who suggested me continuing.
Yeah.
So
Yeah.
it's on you. The fact that there's a second course. So yeah, yeah, no, but yeah, definitely we can work something out, in the end.
Yeah, yeah.
Okay.
Yeah, I don't know if I could probably do a credit overload
Yeah.
for
Well, yeah, yeah, don't stress too much about it, and then you can decide closer to the beginning of the beginning
yeah.
of the semester. Yeah, yeah. Okay.
Yeah, I still have time. Like I could
Yeah, exactly.
drop
Yeah,
a
yeah.
class maybe like I don't know. I'll figure it out.
Good, good. No, perfect.
Yeah. Well,
Okay.
is it also on tensors or is it like
I
on
mean, I'll try to maybe have some relation to some of the stuff that we did here, but the nature of the topological stuff is very different from, it still will be heavy on linear algebra for sure, but
okay.
it does have a different flavor, so there's not going to be that much overlap. If there were some overlap, I would also have to explain some of it during class because
Yeah.
I'm not using it as a requisite. So,
Is it beginner friendly though?
it will be beginner. I mean, it
I don't
depends.
have any experience
Uh,
in topology.
it would be as beginner friendly as this course was. So
Oh, okay.
I don't know if you consider this course beginner friendly or not, but like if you did, then it wouldn't be worse than like this one. You know what I mean?
Okay.
Yeah, yeah.
Whether you would you I feel like I have a strong background in linear algebra
No, no,
now
I
after
mean,
this
like,
course.
I definitely wouldn't, again, like, I wouldn't expect anyone more to know, like, the Calc 3 or linear algebra. That's kind of like so you don't need
Okay.
to know topology. That's what I mean. Yeah, yeah, exactly.
Okay.
But
Okay.
yeah, yeah. But again, sometimes like we will have like some more deep dives, into more like abstract things. But like I'll still kind of like keep the problem less set pretty down to earth.
Like the timings of when the course will run.
Oh yeah, yeah. I sent an announcement about that. It's on the Canvas side. I think it's Monday, Tuesday, Thursdays from 3:30 to the one that's kind of like around 3-4. I don't remember that time block. But yeah, it's
Tuesdays,
like
Thursdays to 3 to
just
4.
look at the Canvas announcement about it. I did send it.
Let me see.
Yeah.
Actually. Let me actually look at this. Um,
Yeah, it's Tuesday, Thursdays, 3:50 to 5:10, if I'm not mistaken. Yeah.
oh,
Yeah, yeah. So check
that
on that.
totally works.
Oh,
Oh,
okay,
wait,
okay.
350 to 510.
I think so, yeah.
Oh,
Yeah,
wait,
yeah.
I would have to move a class because I have a computer architecture
Oh, okay.
class exactly during that time,
Got it.
which is
Got it.
like it's one of the core
Important
classes
ones.
of engineering. Yeah, like you're supposed
Well,
to take it at a specific time,
maybe,
which
I
is
mean, obviously I
annoying.
wouldn't tell you to just move it if there's not like
I want to see. I'll try to find another section
yeah,
if
yeah,
I
yeah,
can.
exactly. If there are other sections that you can consider it, but
Yeah.
if it's important, like,
Oh, I was. Let me check actually right now.
Well, I will close the Zoom meeting soon. Just
Okay.
I have to go to the
Anyway,
office
thank
hours.
you, Professor. Are we coming in during finals for anything?
No, we won't. But again, I'll send you like an email, an announcement with office hours if someone wants to stop by just to chat about
Yeah,
any problems. So
probably
that
like probably when I finish the problems, I'll
yeah, yeah,
probably
yeah,
want to
yeah.
go over
I'll
them
I'll
with
think
you.
about it kind of like at time, but probably after my final for Cup 3 because until then,
Yeah.
yeah, like there's no point, you know. But yeah, I'll send an announcement. Yeah, yeah. Okay.
Okay, cool.
See you.
Thank
See you.
you.
Bye, bye.
See you, Professor.